Welcome to Lecture Module 3, Part 2, Controllers Based on Finite State Machines, and this is for ECE 337 ASIC Design Lab, and I am Dr. Mark Johnson. First, I'll give you a little bit of definition of what I mean by a controller. I am referring to devices that control various sequences of events. It may be controlling a protocol for a communication interface, which is the type of application we are going to focus on the most in ECE 337, but you have controllers in many situations, a lot of embedded applications, automobiles, appliances, aircraft, etc. But pretty much anything that involves a defined sequence of events, and particularly if they are subject to some user inputs or sensor inputs that determines what the sequence of events should be, that would be an application of a controller. And there are a number of ways of implementing this functionality, and when you are designing something, you'll have to decide what's most appropriate for the situation. A very common way to implement controllers, especially in embedded applications, and again, the automobiles, appliances, that sort of thing, is that you would use a microcontroller and you would develop firmware for that microcontroller that would monitor inputs to the microcontroller that are probably coming from sensors or user input, and it would have outputs controlling various functions of the system. However, there will be cases where custom logic is needed, which is our focus in 337, and that could be used on an ASIC or a system on chip, could be used on an FPGA, or even some very low-end reconfigurable devices called PLDs that we used to use in ECE 270. Here is a top-level block diagram of a general purpose controller. This design wouldn't work for every possible application, but there are probably a lot of simple applications that could follow this kind of template. And it consists of, well, primarily a state machine. That's really the heart of it. That's where you define the sequence of events to be produced by the system, as well as how those events are controlled by the inputs. Of course, you need inputs to the system to determine the control of the events, and those would normally be asynchronous inputs, particularly if they're coming from the outside world or coming from off the chip. They would be asynchronous, and in that case you would need synchronizers before you allow those inputs to go to the state machine. It is also likely that you would need to control the timing of some of the states. You might need to hold a given state for a certain amount of time, and you can use clock dividers or you could use timers to control this. Now, clock dividers we've already talked about. A counter that hits a rollover value and just keeps repeating that pattern, generating a pulse each time. On the other hand, in some cases, you just need a single event timer, in which case the control unit would send it a signal to tell it to start. It would count up to some value and then send a pulse back to the controller to tell it that that value was reached. So if you need one particular state or just certain states to be held for a certain length of time, this could be very useful for that. Before we go on, I want you to stop and think a little more about the need for the synchronizers. What if this did not have synchronizers? What could go wrong? I'll pause a moment for you to think about it, in the live lecture, we would discuss it together. Well, in the absence of synchronizers, if an input happens to arrive too close to a clock edge, causing a setup or a hold violation on the state register in the state machine, you could send the state machine into some unpredictable state. And if the state is unpredictable, it means that the control signals that it's sending to various devices will be unpredictable. If this is controlling a communication protocol, well, it's going to mess up the communication. But if this was controlling something safety critical, that could be a very bad thing. So synchronizers would be at least one of the protections that you would need for scenarios like that. And this is just a summary of what we discussed moments ago. I want to spend a little more time thinking about synchronizers and why we need them. So you know how they're designed. They're very simple. Two flip-flops chained together. You already know how to write the Verilog code for it, but I would like to make sure you have a little better understanding of the behavior of them. First, I'm going to consider what would happen if we just have a single register receiving an input. So I have a value called WPTR. It's a 4-bit value, not just 1 bit. It gets stored in a register, and then there's the output of the register. Well, in the timing diagram that's drawn below here, I've deliberately set it up so that one of the bits of the input, WPTR, falls right near the active clock edge, bit 3, and as a result it causes bit 3 of the output of the register to be, well, either metastable or simply an unpredictable value, 1 or a 0. The amount of time something is metastable is random, although typically it will settle out before the next clock edge. But I do also want to emphasize the fact that it's unknown does not necessarily mean it is metastable, although in a scenario like this it very well could be. So here is an illustration of how the synchronizer behaves subject to a timing violation of the input. So I have an input, arrives very close to the clock edge. The output of that first flip-flop goes metastable initially, settles out to a 1 or a 0, but you don't know which one it's going to settle out. And at the next clock edge, whatever value is at the input will get cleanly captured by the input. So here input is a 1, or excuse me, in is a 0, we hit the clock edge, the 0 gets latched by the first flip-flop. So it's just during this one clock cycle that the first flip-flop is metastable and settles out randomly. Now, the second flip-flop has the output that's just called out here, and you'll notice at the output you never see any metastability. Reason being, at this clock edge, the output of the first flip-flop was 0, so that gets stored and appears at out. We get to the next clock edge, and the value of foo, this intermediate signal, is either a 1 or a 0 at this point, but we don't know which it is. So the value of out ends up being an unknown or unpredictable value, but it is a stable value. The first flip-flop will settle to 1 or 0. So whatever happens, this will not end up being metastable. Although the fact that it's unpredictable, depending on the application, could be a problem. And in fact, in this case, the input, because it's asserted to 1 such a short time, might be completely missed. It's shorter than the clock cycle. If the first flip-flop settles out to a 0, you'll end up with a 0 at the output. You would never know there was any kind of pulse on the input. Well, really, you don't want to be trying to sample inputs that are changing faster than the clock of the system. Even if you didn't have metastability, you are at considerable risk of missing values on the input if they're changing too frequently. But if this input was held a longer time, then the value of the input would eventually make it to the output of the synchronizer, within a couple clock cycles at least. And the fact that the first flip-flop is metastable and settles out randomly doesn't necessarily hurt anything, because the only consequence of that metastability, if in is held long enough, is that it just causes a variation in the amount of time it takes for the input change to appear at the output of the synchronizer. And for example, in things like serial interfaces, there's going to be a little bit of variation in the timing of the changes of the serial data anyway. The effect of the synchronizer is to introduce a little bit of additional timing jitter, but if you have enough margin for the timing in the design of this, the variation in the arrival of the transition at the output of the synchronizer may not be a problem at all. But I've got something a little further for you to think about, and this relates a bit to the previous slide where I had a multi-bit value. Is a synchronizer sufficient for more than 1 bit inputs? And of course, if I have more than 1 bit, I'm going to assume that I have multiple synchronizers, 1 synchronizer for each bit of the input. But even if I have multiple synchronizers, 1 for each bit, is that good enough when you have multiple bit valued inputs? So the hint here is, well, what if you have a bus, it's multiple bits, and it's carrying a number? So it's carrying a value where each of the bits should correlate with each other. The value of all of them combined gives you the value you're interested in. So just 1 bit by itself is not the relevant information. It's the collective value of all those bits together. Okay, so with that in mind, is it sufficient? I hope that you said no, because metastability and timing violations are not necessarily going to occur for all of the bits. For one thing, the changes of the signal on the bus for each bit on the bus will not necessarily arrive at exactly the same time. So some bits may cause metastability, some bits might not. What's more, even if they all caused metastability, some bits will randomly settle to a 1, some will randomly settle to a 0. So what you end up with is, even if no metastability gets through, the fact that you've got bits where the value is unpredictable means that you're going to have, well, at least a clock cycle period where the value coming out of the synchronizer is garbage. So yeah, so if you're using synchronizers to, let's say, synchronize multiple bit numeric values, you're going to need to do more than just a synchronizer. You may still need a synchronizer, but generally what you end up needing is some kind of handshaking signal that says that I've asserted a value at the input and that after a certain amount of time that value is guaranteed to be stable and be correct. So typically you just need an extra signal that says, like data ready or strobe or something like that. And in fact, you will do something like that in lab 7. I have a couple really basic guidelines, or I would go further than saying guidelines. I would think of them as rules that you should follow as you're designing a controller. And really, this isn't just for controllers. Any of the logic we design should normally be implemented this way. Someday you may discover exceptions where you have to do something that violates these rules, but you have to have a really, really good reason, and usually it has to do with pushing the limits of performance on a circuit. But what the rules are: 1, all components in your module or your system must use the system clock as their clock. And when I say all components, really that's referring to the edge-triggered flip-flops. Those would be the only components in your circuit that should be using the clock. But all of them should run from the same clock. Violating that rule leads to enormous headaches. It makes timing analysis of your design much more difficult, and it makes your design very susceptible to variations in delays of different logic gates that lead to somewhat unpredictable arrival times for clocks. And given the hazard of hold times, well, setup time violations are bad, but there are workarounds for them. But if it results in hold times, your chip is really useless, or at least useless for the situation that causes this to occur. Another rule: any of the outputs of the modules in this controller design, which you've got in the example I gave, the only blocks feeding inputs to the state machine are the timer and the clock divider. Those outputs should not be used to directly clock anything. And in fact, that really follows from the first rule. Instead, those should be used as inputs to the next state logic for the state machine. And really, in any kind of sequential system design, signals like that, timer signals, clock divider signals, or really any other signal produced by a block in your design, should not be used to clock anything. Instead, it should be used as a control signal to the next state logic for the register or the flip-flop you are wanting it to affect. For the remainder of this set of slides, I'm going to go through an example of a very trivial controller. In this case, it's more of a do-nothing machine. It's just that I wanted to create something small and simple enough to do in a short time and still explain some of the concepts regarding the way a controller works, and particularly the way the state machine interacts with timer blocks. So this timing diagram, as well as the state transition diagram, illustrate how this design is intended to work. I think I will explain it in terms of the state transition diagram first. I think this representation is maybe a little more intuitive, at least to me, and that is that an asynchronous reset forces the state machine into an initial state, and in this design, for whatever reason, we want it to wait one clock division period before it goes to a state where it's going to trigger the other timer block. So I'm in the init state. I just have a transition that's conditional on the output of the clock divider. So this is another way of representing what I said about the rules for use of the outputs of timers. Is the output of the timer or the clock divider is used as a control signal for a transition of the state machine. It's not used as the clock input to it. But it has the effect of determining when the state transition occurs. So we go into a trigger state, and in this state, I've said that an output called trigger will be asserted. And if you looked back at the block diagram, trigger is the name of the signal that goes from the state machine back to the timer block. So it causes the timer to start counting, and the state machine itself then, just on the very next clock cycle, goes to this wait state. So if you look, the transition does not have a condition on it, which means on the very next clock cycle, it's going to go to this state. So the next state value from trig is always wait. Okay, so we're in the wait state. This time, I'm waiting for the timer to finish its job and output a pulse, and the signal happens to be called tim out. No, that's a typo. That should have been timeout. Oh well. So when it sees the timeout pulse, it goes to a finis state and then asserts a signal called done. And this state machine is designed so that once it reaches this final state, it stays there. Now, even though this particular design is not useful, there are occasions where you might want to do that. Let's say you're implementing a power on sequence for a system, where on a reset, let's say you want to turn this module on first, then turn on that part, maybe turn on an external device after that. You will have systems where the sequence that you turn the power on, it can be very critical, but it's something that once everything is on, you're done. You don't need to do anything else. So the state machine could just reach a final state or a terminal state and stay there until the next reset. So this is at least an illustration of that. Now let's look at the timing diagram and see how it represents this. We've got a clock that's continually running. The clock divider is generating a pulse every, well, 10 clock cycles. Now I'm not showing all the clock cycles in the diagram, but every 10 clock cycles we get a pulse that is of 1 clock cycle duration. And that pulse allows the state, because on a reset the state goes to init, then it sees the clock div pulse, goes to the trigger state, and the trigger output is asserted. The state machine goes directly from trigger to wait. It waits until the timeout signal is asserted, and it happens that we are specifying that the timer counts clock div pulses and counts 3 of them, and that determines the time period that it is being used to count. And so it outputs this pulse. The timeout signal then allows the state machine to go to the finis state, and the done is asserted, and then everything just stays there until the next reset. Now what I'm going to do is show you how I can use pseudocode as part of the process of translating this design from a block diagram and a state transition diagram into code. And when I'm figuring out the design, you may find it more efficient to just sketch out the functionality, because once you figure it out in terms of pseudocode, then it becomes, again, very straightforward to go to the actual Verilog code. So this block represents the actual state machine. It takes clock, reset, clock div, timeout as inputs. It outputs a trigger and a done signal. Has an internal next state and state variable. Here's our state register. Well, I went ahead and wrote that in the Verilog style. It's pretty, or almost the complete Verilog style. It's pretty compact already. And then I've written some code, pseudocode, that just describes the next state logic for this design, so that if the state is an it, then depending on the value of clock div, next state is either trig, or the next state retains its previous value. Okay, if we're in the trig state, we want it to go to wait on the very next clock cycle. So I'm answering the question that's in the comments here. In class, I might have made that a clicker question. When it gets to the wait state, it's waiting for timeout to be asserted, at which point the state machine will go to fini. Otherwise, it remains in the current state until that event. And then finally, when we get to the terminal state, then the next state is the same state, and it will stay there until the next reset. Okay, output logic is really simple. Trigger is asserted, or it's true, when the state register value matches the state code for trig. Done is asserted when the state value matches the state code for fini. So that's what the pseudocode looks for. But something I would like to do is show you how I can translate this into really a schematic representation, but just in terms of registers and muxes. Here goes. I am going to sketch out a schematic of this pseudocode. So I've got inputs clock div 10, I've got an input timeout, clock and reset I'll just show at the register. I've got outputs trigger and done. Okay, well, let's see. I'm going to go ahead and draw the register. It's probably the simplest thing out of all of this to draw. And so it's going to be right here. It's got a clock and a reset on it. Well, that says RST, so I suppose that wouldn't be active low. So I'll let it be an active high reset. And I've got clock. Okay. And I've got state and next state. So let's see. I think I'll write it kind of vertically here, I'll say, because I'm a little shy on the state and next state. Okay. And let's see. I've got my next state logic here, which is this case structure. So a case structure, well, you'll find that really any kind of branching structure in Verilog can be represented in a fairly straightforward manner as a multiplexer. And in the case of this next state logic, it has 4 possible branches, and it's got state as the control signal to do the selection. So I'm going to draw a mux and state is going to be the selector for that mux. And let's see, the possible inputs correspond to 4 states. I'm going to write state names instead of the encodings of them. Init, trig, wait, and fini, which those are the 4 possible values of state. And let's see, there are a couple of these states where the input to the mux is really simple. The trigger state has a next state value of wait. So really, the input to the mux here could just be hardwired to whatever the code for wait is. Similarly, the fini state can be hardwired to the value of fini. Okay, now init and wait are a little more complicated, and in fact I'm running out of little space, so I'm going to move these 2 signals off to the side a bit. I'm going to put clock div 10 up here. I'm going to put the timeout signal down here. And if I look at the init state, the value of next state depends on the value of clock div. So there are 2 possible values. So a single if then else branch like this I could consider as a 2-way mux. So if I have clock div 10 as the control signal for a 2-way mux, and the 2 possible values are just 1 or 0 here, then for the value 1, next state is just whatever the state code is for trig. So we're ending up with muxes with quite a few hardwired inputs. So it's really more like they're implementing lookup tables, except that in this case, if clock div is 0, then next state is going to be equal to state. And rather than draw the line around here, I'm just going to show that state is the input to that. And then the output of this mux becomes the next state value for init. And I hope you can stare at this a little bit and convince yourself that what I've drawn here implements the logic here. Okay, timeout is controlling whether next state is fini or current state. So I'm going to let it control a mux. and the output of that mux is going to be the next state when state is wait. And again, it has a 1 or 0. When timeout is 1, the next state value is fini. When it's 0, the next state value is the current state. So again, I'm just going to write state right here. And let's see what's left. We've covered all the next state logic. So what you see, four-way case gave us a four-way mux. Two-way if then else gave us a two-way mux. And the conditional expression ends up being the control line for the mux. And then the values being assigned inside the branches of the if then else end up determining the inputs to the mux. Okay, we've got everything except the output logic. And once again, I didn't plan this out on a vertically oriented whiteboard so well. I am going to have output logic for trigger. And it's just going to be combinational logic that determines if state is in fact equal to the code for state trig. So the state signal is going to go there, and for the done signal, equal fini. And then that, if that's true, then done is asserted. One thing I omitted from here was the number of bits. We have 4 states that would take 2 bits to represent. And so the state signal is going to be 2 bits. But that also implies that all of these state codes are 2 bits. So trig is a 2-bit constant, but it's a 2-bit value going into the mux. State's 2 bits, wait's 2 bits, the next state for wait is 2 bits, fini is 2 bits, 2, got a lot of 2's all over the place. State was 2, oh, next state has to be 2 bits, 2-bit flip-flop. 2 flip-flops. Okay, I think we've accounted for all the signals. So, something I will look for you to be able to do on an exam is at least recognize maybe slightly simpler cases of what's going on here. I probably won't have you draw diagrams of the code, but I may give you choices where here's a diagram. Does this diagram represent this piece of code? Or, you'll have a selection of diagrams, which one represents the code? Things like that. Or I may ask you what kind of circuitry is required to build the code that's presented to you. And you'll find examples of that kind of thing in old exams. Here's pseudocode for another one of the blocks. This one being the clock divider. And let's look at it. So it has input clock. Probably should have a reset input also. In fact, yeah, the register has a reset, but it didn't show the reset up here. But it has an output clock div 10 that will be generated every 10 clock cycles. So we have a count and a next count variable, which end up being the output and the input of the count register. And then I have next state logic, which is really simple in this case because the wraparound value is hard coded. So I've just set this thing up to continuously loop from 0 to 9. So when count is equal to 9, next count is 0, else count is count plus 1. So when the next state logic is as simple as this, a one-liner with the conditional expression works. So in actual Verilog, this could be a continuous assignment statement instead of an always block. And then the output logic is also very simple. Clock div 10, it's 1 when count equals 9, 0 otherwise. So it's just a true-false condition there. Let's look at the question. So in class, again, I may put it 2 clickers or to a zoom poll, but think about, as this thing is running, how long is the clock div 10 signal asserted? Which is also how long will the count be equal to 9, since that determines how long that's asserted. So 0 cycles, 1 cycle, 9, 10, unpredictable. Think about it a minute. Well, do you think it's 0? I mean, when count equals 9, it goes immediately to 0? Well, no, it doesn't immediately go to 0 because next count goes immediately to 0, but then it has to be captured by the register. So it ends up waiting a clock cycle for the change to occur. So in fact, the answer is 1 cycle, or 1 clock cycle. I'll also comment on what the diagram for this would look like. I'm not going to draw all of them, but you may wish to do this as a practice for the exam. We have a register, you know how to draw that. We have next state logic. Well, on the previous diagram I said an if then else branch gives you a two-way mux. Well, a conditional operator really is like a two-way selection as well. It's like an if then else, because if count equals 9, then the output 0, else count plus 1. So this also could map to a two-way mux with 0 and count plus 1 as the inputs to be selected, and count equals 9 providing the control signal for the mux. And then clock div 10 just needs a simple combinational block that gives you a 1 only when the count is 9. And then you ought to be able to figure out how many bits the count and the next count are. Hopefully you decide it's 4 bits because 3 bits would only get you from 0 to 7. So you need a 4th bit to be able to count up to 9. I mean, you could count up all the way to 15, except you're not using all those values in this design. Now let's look at a possible implementation of the timer block, again described using pseudocode. So we have clock and reset as an input, and trigger, which is a signal to the timer to start counting, and then we have timeout as an output to indicate when it's finished counting. And it's actually counting the number of pulses that are received on clock div 10. So it's not counting clock cycles, really, it's counting clock div 10 pulses. And if I look at the register code, I've got 2 registers. A 3-bit register based on the declarations here, and a 1-bit register. Now the 1-bit register is really just a registered version of the input clock div 10, and all it really does is protect us against this being a Mealy machine, because this way timeout is derived entirely from values in registers. So going on to the count, the reset value, you'll look, for div temp resets to 0, okay. The count resets to 4. Now why am I doing that? Well, in this particular case, or this implementation, I'm using 4 as a value at which the counter waits until a trigger pulse is received, at which point the count is then set to 0, and it proceeds counting up from 0 until it reaches 4 again, and then it's not going to go further than 4. So we reset to 4 as the state that it's going to wait at. So really 4 is like a wait state. Let's see, normally count is going to take the value of next count, and we mentioned div temp is just a registered value of clock div temp. So here, the next state logic, again, I can describe fairly simply in terms of conditional assignments. Well, I say fairly simply, it's 2 layers of them. This might have been a little neater with an if-then-else structure. But in any case, what we're saying is the next count value, when the trigger is asserted, the next count value is 0. But if the trigger is not asserted, the next count value is going to depend on clock div 10, on whether or not the count is less than 4, because remember, we only want to count clock div 10 pulses. So when clock div 10 is asserted, well, and count is less than 4, it's going to allow the count to increment. So each time it sees clock div 10, until the count reaches a value of 4, it's going to increment the count, which means it's going to assign the next count value, and then that will get stored to the register. Once the count reaches a value of 4, it's not going to matter if clock div is asserted, because this expression will be false and the next count will be count. So it will just hold at a count of 4 until the next time. Well, in this design, it's never going to see another trigger, but maybe in some other design, it would be waiting for another trigger pulse. Output logic. I wanted it to produce a pulse after the third occurrence of clock div 10. So I said, okay, timeout is asserted when count is 3, and I used div temp instead of clock div 10 just to avoid mealy machine type of operation. So there's the pseudocode for this. I would say, you ought to be able to sketch out a schematic for this as well. There would be a couple of registers, 2 two-way muxes. One is a mux that chooses between 0 and the output of a second mux. The second mux is choosing between count plus 1 and count. And then the output logic is, again, a very simple combinational logic function. Last slide. Really, it says design tips. Now there are 2. So the most important one, I would say, is that if you are dividing down by a large number, so let's say the increment logic in the counter is too slow. If the number of bits we're counting, or the range of values counting is large enough, that may become a problem with timing delays, and so we can divide the counting across more than one counter. So the first counter can count up to the same value over and over. It could count to 10, and then you'd have another counter that just counts the pulses from the first one. So one counter counts the individual cycles every 10, produces a pulse. The next counter counts every 10. And you could chain counters in this way, and in fact you will probably do something like that in the timer for the UART design in Lab 6. Of course, each counter we still need to obey the design rules that I've told you before about only using the external clock as the clock signal for the register. And any other control signals go to the next state logic. Okay, the second tip I would say is not quite as strong a tip, it's just more of a design preference that I have, and that is when I'm generating control signals or timing signals, I like making them 1 clock cycle in duration. So whatever event they trigger can only happen at that 1 clock cycle. What will happen to you, I think a lot of students will tend to have a signal asserted the entire time. So like a timer, instead of having a timeout signal, they'll just have the timer assert an enable signal that stays asserted the entire time that the state machine is waiting. And so the state machine would wait for that value to go low again. So students will tend to use level sensitive signals where it'll hold the value for whatever the length of time of interest is, and they will wait then for it to change back to its disabled state or 0. A lot of the time that works equally well, but you will occasionally run into situations where you end up needing to do synchronous edge detection on an enable signal to figure out whether, say, to change states. So that's it.